Good morning, everybody. I warmly welcome to all of you in the series of Mechanics of Solids. Now, let us recall what we did study up till now in the previous class. In the previous class, we have understood what is the meaning of shear stress. We have understood how the shear stress distribution diagram can be plotted for different sections, just like rectangular section, circular section, etc. So in the same series, we are going ahead and let us be understood how the shear stress distribution diagram can be plotted for different section like unsymmetrical I section, triangular section, etc. So we learnt in the previous session about the shear stress, we derived the equation of shear stress, we solved the certain problems related to the basic fundamental equation. And today's objective of the session is define the shear stress, draw the shear stress distribution diagram, specifically unsymmetrical section, unsymmetrical I sections as well as triangular section. Let us revise what we studied in the previous class. We have been seen in the previous session about bending stress and beams. We have seen that a part of a beam is subjected to a constant bending moment and zero shear force. There will be only bending stress in the beam. The shear stress will be zero as shear force is zero. In actual practice, a beam is subjected to a bending moment which changes from section to section. Also, the shear force on the beam is not zero. The interesting point, the shear force is not zero, especially beam is concerned. It varies from section to section. Hence, because of this shear forces, the beam subjected to the shear stresses, and right now we have to study this shear stresses and we have to study what will be the variation of shear stresses along the length of a beam along a particular section. So, in the previous class we have also derived an equation of shear stress, specifically tau is equal to Fa y bar by Ib. Please refer this PPT. Tau is equal to Fa y bar by Ib, where F, which is the acting shear force at a particular section, I we know moment of inertia, B width of a section, A y bar, it is a combined term. If we are taking care, it is nothing but the moment of area of a figure at level EF from the neutral axis. So now, especially today we are going to discuss how the unsymmetrical I section we can plot the shear distribution diagram. Starting with the problem, the shear force acting on a beam at an I section with unequal flanges is 50 kilonewton. The moment of inertia of the section about neutral axis is 2.849 into 10 raised to 4 millimeter raised to 4. Intention is the plotting of shear stress distribution diagram and find the important values at particular points. And the figure which has been given to us is this one. Carefully visualize over here that in this figure, please refer the top flange having a section of 200 mm by 50 mm, while the bottom flange having a size of 130 mm by 50 mm. So obviously the given section is unsymmetrical about x axis. So our priority, first priority is to find out the CG of a section, and then we have to proceed further to find out the shear stress. So the overall depth which has been given to us is 200 plus 50 plus 50, that is 300, and the width of the flange which has been given 200, specifically top flange, bottom flange width is 130, and all the thicknesses, specifically the web thickness, flange thickness, both, everything has been given as 50 mm. So if you are referring in this given data, the shear force acting at a section which has been given as 50 kilonewton, here it is noted that the moment of inertia which is given to us. Now, if this moment of inertia is not given to us, we have to find out by using the basic principles, parallel axis theorem. We have to find out the moment of inertia if it is not given to us. So now our step number 1 is to calculate the position of CG. This is the procedure. Let y bar is the distance of the CG of the section from the bottom flange. Y bar, distance which has been given from the bottom flange. So y bar is equal to a1 y1 plus a2 y2 plus a3 y3 divided by summation of all three areas a1 plus a2 plus a3. Now let us be understood what is a1, what is a2 and what is a3. Let us switch ourselves to this over here tabletop. This is the given section. All the thicknesses as given as 50 mm. This has been given as 200 mm. This is of 130 mm and the web height is of given as 200 mm. We have divided into three different rectangles, number 1, number 2, number 3. So we have divided unsymmetrical eye section into three different parts to find out the CG or centroid of the section. We are assuming this is as y bar. So a1 is nothing but the area of the first part, a2 is the area of the second part, a3 is the area of the third part. y1, y2, y3 are the distances of the CG of the area to the reference axis. Right now we have taken care this bottom part of a flange, is taken as a reference axis. So y1 is nothing but distance of CG from the first area to the reference axis. So this is my y1. If this is the CG for second figure, then this is the y2 and this will be the CG of the third figure. Then 50 by 2, that is the 25, is nothing but my y3. So overall a1 is 200 by 50, y1 is 50 by 2, that is 25 this distance, plus 200 plus 50. A2 is the area of wave, that is 200 multiplied by 50, that is the wave thickness. y2 is the distance of the CG of the second area. Now the CG which is acting as 200 by 2, that is 100 mm, plus 50, so 150 is y2, and a3 is nothing but 150 into 50, while y3 is the distance of CG, that is a 50 by 2, that is my y3 distance. So if we come back to our PPT and refer it out right now over here on this PPT, that is a1 y1 plus a2 y2 plus a3 y3, starting here the started from the bottom side. So a1 they have been considered in this PPT is from the bottom side. So a1 y1 a2 y2 plus a3 y3 divide by all the summation of the areas. We found out that distance is of 166.51. That is a distance from a neutral axis to the bottom flange. So the top flange distance is 133.49 mm from the top. So if you refer the figure, that this is the neutral axis and the distance from the bottom flange is 166.51 mm, while from this neutral axis to the top flange the distance is 133.49 mm. So now next procedure, the step number 1, shear stress distribution on the top flange. Our intention is to find out what will be the shear stress distribution on the top flange, specifically on the top fibers of a flange, then connection between flange and web, then at the neutral axis where we found out the maximum. Then we have to found out between connection between the web and the bottom flange and the bottommost fiber. So if you want to refer this over here on this tabletop, our intention is to found out, please refer the tabletop. Here we want to find out what is the variation over here. Obviously we know it is 0. Then we want to find out the connection between this flange and wave. What will be the variation? We know it is parabolic variation, we have already been studied in the previous class, and this is the variation. Then we have to take the variation between wave and flange. It's very high value. Then we know at neutral axis, once again a high value. Then at the bottom part, connection between this web and flange, the value is over here. The remaining value is for between flange and web connection, and 0 at the bottom flange. So our intention is to find out the variation at different important points, and that we have to calculate all these things points, and then we have to plot the shear stress distribution diagram. So please come to this PPT. The first one parameter, that is the shear stress distribution in the top flange. Now it is known that the shear stress is 0 at the top of the flange. Shear stress at the junction of the upper flange and the web is given by tau is equal to Fa y bar by Ib. So now let us take the first part, what will be the variation of shear stress between these two junctions. Please refer this PPT. Now here A y bar is nothing but the moment of the area of the upper flange about neutral axis, which is nothing but the area of upper flange multiplied by distance of the CG of the upper flange from the neutral axis. Please take and understood this one over here on this tabletop. This is the figure which has been given us in the data. Intention is to find out the variation over here at this level. So the area under consideration is this one. This is my neutral axis, and this is 133.49 mm that we have been found out using the concept of the center of gravity. CG is over here exactly at the center. So now AY bar is nothing but the area 200 multiplied by 50 multiplied by Y bar. Y bar is the CG of the area under consideration to the neutral axis, that is 133.49 minus 50 by 2. This is the AY bar we have to use in the computation in our simple equation tau is equal to Fa y bar by Ib. So refer the PPT please. Then in this case AY bar will become 1084900. Now B is the width of the flange, that is 200 mm width of the flange. If you refer the figure over here, our intention is to find out the variation at this level. So width is available is this one, that is the width of the flange, that is of 200 mm. So tau is equal to Fa y bar by Ib, F which is known to us, which is given in the data, that is of 50 kilonewton, that is of 50,000 Newton, multiplied by AY bar that we have already been found out in the calculation, that is of 1084900 divided by IB, I already which has been given in the data. If it is not given to you, we have to find out by using the basic concepts of moment of inertia by using the parallel axis theorem, and B 200 is known to us. By solving this simple equation, we achieve is 0.95 megapascal Newton per mm square, that is the value of tau. So this value which is shown over here on this figure, then please come on to this. This is 0 over here, this is variation, and this variation is parabolic 0.95. This value is 0.95. This is the variation of shear stress at a section, specifically at the junction between the flange and a web. Now next point. Come to this PPT. Shear stress in the web just at the junction of the web and the upper flange, which is suddenly changes. So if you refer your I section, it is the characteristics of an I section that this width changes suddenly from 200 to 50 mm, and because of that the shear stress which has been taken care by the web at a junction is suddenly high compared to the junction between flange and a web. So over here please note down these things, that shear stress in the web just at the junction of the web and the upper flange, which suddenly increases from 0.95 megapascal to 0.95 multiplied by 200 divided by 50, means it varies. This is the width of flange, this is the thickness of web. So width of flange and the thickness of web, the ratio, as per that the variation of the shear stress suddenly increases at the junction, that is 3.81 megapascal it will become. So if you want to refer over here in the figure on this tabletop, this value is 3.81, suddenly increases. So 0, then 0.95, at the same junction the value is of 3.81 Newton per mm square. As we go ahead, so we achieve 3.81 megapascal. Now the shear stress is maximum at the neutral axis. This fundamental we know very well. Hence the shear stress at neutral axis is given by